Okay, all good. All right, can you see the slides? Yeah, good. Okay, let's continue PN junction under illumination. So we have discussed last time about thermal equilibrium condition, and we have discussed that when thermal equilibrium is reached, we're going to have only one single Fermi level, right? So upon illumination, we've also covered in the last class, we're going to have a gradient of minority carriers, excess carriers generated in the device, okay? So that will cause the carriers to flow again and become a minority carrier on the other side, okay? On the other side of the junction and waiting to be illuminated, waiting to be collected. So we have also discussed the spatial generation last time and the general solution given by the below equation, which is also applicable to delta nx. Okay, you just have to switch the LH to LE here, and then the tau H to tau E, right? Quasi-neutral region. Okay, so we've also covered the dark current and light current, dark current and illuminated current, right? So we've also seen the JV curve or the IV curve for dark current and JV curve for the illuminated current. So if you can recall, we've discussed in the previous class about this curve and also about this curve, right? Dark versus illuminated current. Dark versus illuminated. And the JL is given by this equation, Q times generation times the summation of diffusion length of electrons, diffusion length of holes, and the width of the depletion region. Okay, so this shows that the light generated current JL has a value equal to that expected if the carrier is generated by light in depletion region and within minority carrier diffusion length of both sides can contribute to it. Okay, kita akan tengok in this lecture, we're going to see how do we then design the PN junction position, PN junction position, in order to ensure that all of the carriers can be collected to the outer circuit. Right. So when you talk about PN junction under illumination, so the most straightforward device that you can relate with is a solar cell. Because solar cell is a PN junction device which works under illumination. Okay, we have discussed about the EPH over EG last time, EPH more than, equal to, and stuff like that. So for a solar cell, the incident energy of the photons need to be equal to or more than the band gap in order for us to generate electron hole pairs. And these electron hole pairs need to be separated at the junction. Okay, need to be separated at the junction, and then they need to be collected on both sides of the junction. Okay, so it involves light absorption, it involves carrier separation. Sorry, it involves light absorption. It involves carrier generation. It involves carrier separation, and then it involves carrier collection. 4 steps: light absorption, carrier generation, carrier separation, carrier collection, in order for you to get your IV curve or JV curve. Okay, kalau you tak dapat, if you don't successfully go through these 4 steps, you won't see a good performance of the device. Okay, on the other hand, you'll probably see nothing or a very poor performance of the device. Okay, so now we're going to look at the actual collection probability of the light generated carriers. So the carriers are generated by the light upon illumination, and then the carriers are then separated by the junction, and then the carriers are then collected. So we're going to see how good is the collection probability. Okay, so when you talk about probability, what is the spectrum of the value of probability? So it ranges from, when you talk about a probability, any probability in general, so the spectrum is 0 to 1, right? Okay, 0 to 1, good. So it's 0 to 1. So you either collect nothing, 0, or you probably collect everything, okay, 1. So that is the extremes that we can have in our device, from our device. In the real case, our collection probability is usually in between. And the collection probability is always dependent on the wavelength as well. Remember last time when we talk about solar cell, briefly, we talk about the solar spectrum, right? And then we talk about UV, we talk about a portion that is visible, and then we talk about another portion that is IR as well. And this is all wavelength related, okay? So photons may come from this region, photons may come from this region, photons may come from this region, okay? So you want to absorb everything in the light absorbing device like a solar cell. And when you absorb the light, it will generate the corresponding electron hole pairs, and you want to collect the electron hole pairs from throughout the device as well. So we're going to relate later on how is this device thickness related to the wavelength of the incident spectrum eventually. Okay, sekarang kita tengok this one first. So here the collection probability is on the y-axis 0 to 1, or if you want to plot in terms of percentage, then you can plot from 0 to 100%. If you're talking about percentage, else you're going to plot 0 to 1. Okay, so the actual case looks like this. Okay, the x-axis is the distance into the device. Okay, into the device means you have to draw the device first. Say the traditional solar cell has an N emitter on top, then P a wafer. Okay, and we discussed a couple of times already that the typical depth of this layer is about 200 or so nanometer, and the whole wafer is usually around 180 micron or 200 micron, close to. Okay, but the wafer thickness is in micron. Okay, micron, but this guy, the top layer here is only nanometer, so it's like 3 orders of magnitude lower in thickness. Okay, so that's the real that's how a real device looks like. Okay, so the distance into the device means the distance into this. So here will be 0 if you flip the x-axis 90 degrees. X-axis dekat on the graph is like this. If you flip into the device, it's gonna be like this, right? The depth into the device. So here means increasing x into the device. Okay, then if you look at the graph, this one will be the front surface of the device. This one will be into the wafer thickness. Okay, so the AB there, the AB here will be the end of your depletion region. Okay, kita flip the device, the wafer yang saya draw kat sini, just flip it 90 degrees anti-clockwise, and you're gonna get a graph more or less. Okay, so A and B are the edges of the depletion region. So this is the imaginary junction of your PN. So in this case, if you look at the graph, the P will be on top. Okay, the P will be here, the N will be here, right? So P will be on the front surface, followed by N. So okay, the property of collection of light generated carriers is unity if the electron hole pair is generated in the depletion region and falls off exponentially away from this region The K constant of this fall off is the minority carrier diffusion length. So if you manage to generate your electron hole pairs in the depletion region, the collection probability of the carriers will be equal to 1. So basically, whatever you generate in your depletion region will be collected. Okay, so that's what it means by probability of collection probability of equal to 1. So you can collect, you can successfully collect the carriers generated in the depletion region. But if the carriers generated away from the probability of carrier collection reduces accordingly. So if you look into the N region, for example, on the right hand side, then the collection probability falls off exponentially. And this exponential factor will be governed by the depletion, by the diffusion length of your carriers. Okay. So on the other hand, if you look at the P side, the collection probability will be reducing exponentially as well. So depending on the diffusion length of the carriers. Okay. So now if you look at this, why does it look like this? Kenapa dia punya, if you look at the N region, for example, N region, so why do we care about the diffusion length of holes? Why do we have to look into the exponential component of negative x over LH, diffusion length of holes, right? So why do we, where do you want to collect the hole actually? So let's get this right first. Why do we bother about hole in N side? Why do we bother about electron on P side? Where do you collect the holes? Okay, minority carriers, okay. But Haziq, where do you want to collect the hole? Do you want to collect the hole on the left hand side or on the right hand side? Left hand side is the P side. Okay, ni P side. P side is the left hand side. Right hand side is the N side. So where do you want to collect the hole? On P side or on N side? For anyone else? Okay, I'm going to say it right. Haziq said right. Okay. Other answers? Kita nak hole pergi mana sebenarnya? So remember last time, just now, I talked about 4 things need to happen, right? 4 things need to happen. Absorption. We're going to learn this in solar cell later on, more specifically. Light absorption, and then carrier generation. EH generation. Third one is what? Carrier separation. Fourth one is carrier collection. So after the generation, you want to separate the carriers at the junction. So the junction is there. Okay, I'm going to say it left. Okay, I'm going to ask you why. I'm going to have to ask you why. Just now you say it right? Right? It's not left. Okay. Now we're going to separate the carriers. So the junction is there to separate the carriers. So how does it separate the carriers? So Amiro, kenapa you cakap left? Amiro, you can unmute yourself. Kenapa left? Where do you wanna? Okay, my question was hole kan? Kita nak collect hole kat mana? Left hand side or right hand side? What do you think?
Dekat left side.
Okay, you said left. Why left? The answer is correct, but why left?
Sebab kita nak kumpulkan semua hole dekat P
Okay,
P side.
we want to collect all holes on P side. Okay, so you say it like this, right? Holes, arrow pointing to the left. Electrons. This is the collection lah. We want to collect holes. We want to collect holes to collect electrons to the inside. Betul? Betul kan? This is what you said, right?
Yeah.
Okay, right. How about others? Haziq, why you said right?
Saya fikir pasal apa tu minority carrier. Apa tu apa namanya? Saya lupa apa benda tu. Tapi yang pasti apa sepatutnya
Minority
kalau
carrier.
sekejap movement minority carrier sepatutnya kita akan apa consider minority carrier. Saya fikir
Minority carrier punya flow.
yes.
Just like last time, right? Exactly last time.
I'm focusing on that.
Okay. In the solar cell, we're gonna see that in the solar cell, we want to collect. Okay, tak apalah, yang previous one is the basic that you've learned. In the solar cell, you want to collect the excess carriers. Macam Amir cakap tadi tu. You want to collect hole to be on the whole side, electrons on the n side. Okay, well, why is that the case? Because we want to minimize the recombination. Okay, so maybe it's not obvious yet. So we're gonna see later on when you collect this hole to we want to collect this hole to be on the positive side, on the p side. Okay, and you want to separate your electrons on the n side. Okay, so when you talk about a solar cell, the carrier separation takes place this way. At every point you generate electron hole pairs, electron will be withdrawn on the n side, and hole will be withdrawn on the p side. Okay, so that's why we said that when you generate your carriers near to the depletion region, your collection probability will be unity, will be 1.0 what will be 1 basically. So if you are away from the depletion region, so the journey of the carriers to get to the depletion region will probably encounter some level of recombination as well. So the further away it is from the depletion region, the more the probability of recombination. And that's why we see the collection probability falls off as it gets away from the junction. So that's why the diffusion length on the left-hand side, on the right-hand side, is for the hole, because you want to collect the hole on the left-hand side. So the further away it is from the depletion region, the probability for it to arrive and get collected is lower and lower. Okay, because you want it to be collected on the other side. Maksudnya, this diffusion length is with respect to the other side, which is the destination of the hole. And the same goes to electrons as well. So you want the electrons to be collected in the n side, but if you are away from the depletion region, say you are generated here, the electron hole pair is generated here. So you want to collect the electron in the n side, and since it's quite far away, so the probability of getting collected is only this much in the n side. So the far it is away from the opposite side, so the probability of getting collected will be lower and lower and lower, because the carriers need to face more and more recombinations throughout the distance. Okay, so bottom line, you want to collect electrons in n side and holes in p side. So the moment they are collected, so electrons already in the n side, holes already in p side, they are already the majority carriers, right? So they are already the majority carriers, and therefore recombination can be minimized. So when you talk about the junction in a solar cell, okay, kita belum discuss solar cell lagi. So this is talking about how do you then design your PN junction? Two cases. Okay, so junction in solar cell, we have discussed when we talk about the generation and recombination lecture last time. It was discussed that the photon flux in the solar cell material falls off exponentially, right? The G factor, remember last time? The generation rate falls off, okay, exponentially with increasing distance, increasing the depth into the material, X. This is the G, or you can call it as flux as well. So from the illuminated surface, so Gx is strongly peaked at the illuminated surface, and this is the surface location, if you like, and this is into the device. Okay, the short circuit current we discussed briefly before we talk about the actual device. We discussed about the IV curve for a solar cell briefly, and this is the open circuit voltage, and this is the short circuit current, GSC, will be given by it can be approximated as the JL, or light generated current. So it is equal to Q times the integral of 0 to infinite of the flux times the generation rate in the device. So if you look at this equation, we can tell that the JSC, the short circuit current, will be maximum when the flux is maximum, and the flux is maximum when the depth is 0. The depth is 0. Okay, is close to unity near the surface, the junction. Therefore, the junction should be close to the illuminated surface. Since we discussed in the previous page that the unity of collection will be 1 at the junction, and the flux will be maximum at the junction, will be maximum at the surface. So combining these two facts together, we need to then design our PN junction to be very near to the surface in order to produce maximum photocurrent in the device. So let's look at these two cases. Okay, case number 1. So this is your flux, the blue one, the Gx. So case number 1 is by red curve, for example. This is your depletion region, AB. And then the second case is the black one, depletion region as well. So you can translate this curve on the physical wafer, on the physical junction. So the red one will be closer to the surface. The case number 2, the black one, will be deeper into the surface. Okay. So if you want to compare the red one, so saya pakai color merah, nanti confuse lah. Red versus black. Okay. So if you compare this junction for red versus black, say this one is P-type, this one is N-type, P-type and N-type, which one would you think would produce higher photocurrent density in the solar cell? Oh, saya label ni terbalik eh. Saya label ni terbalik with the slide. No, I'm going to say left, okay? Lagi? How about others? The red curve or the black curve? Forget the 1 and 2. Forget number 1 and number 2. Red or black? Red. Okay, lagi? Kat biru black, red juga. Okay, red. Okay, lagi? Red. Why did you say red? Kenapa red? Black, okay. Seorang je cakap black. Juara cakap black. Okay, the red, red. Okay, how about others? Why red? Rafai, why red? Oh, 155 dah. So fast. Okay, we'll finish in a few minutes. Kenapa red? Oh, Juara, why is it black? Do you want to design your junction near to the surface or deeper into the surface? Amiro said area under the graph integrated is bigger than black. Area under the graph integrated. You mean with GX? Integrated with GX, huh? Okay. So does it make sense? Makes sense, right? If you look at the equation up there, JSC is equal to JL, then it involves integration of the two curves then. So it involves the junction punya collection probability there with the flux GX. Okay, flux tinggi kat mana? Where is the location where the flux is maximum? Tengok kat blue curve tu. Where's the maximum point of the flux? Near the surface, right? And the flux shows an exponential decay. So you want to design your, So you want to design your junction near to the surface. So for case case red and case black, so the red design, if you like, will produce higher JSC. Okay, higher JSC in the device theoretically. How deep or how shallow? Itu susah nak jawab sebab if you go too shallow, then we get another factors coming in. If you go too deep, then we have another factors coming in. And we want it theoretically by this equation. You want to design a shallow junction. Kita nak junction tu cetek je, very thin, so that you punya current punya integration equation will be maximum. But there's always a but. Okay, there's always a but. But ni kita akan discuss dalam device. But as of now is only you want to go with a very shallow junction design. Okay, nanti kita akan tengok in the device design, the actual case, if you want to go shallow, but if you go too shallow, then that will happen. You want to go slightly deep, but if it's too deep, then so it's going to be, when you talk about the engineering of the device, it's going to be many trade-off. You will get this, but you will lose this. On the other hand, if you go the other direction, you will get this, but okay, there's always a but. So this but is the whole engineering stuff. Okay, so we'll come back to this. So the last slide for this topic, the depletion region has been ignored in the analysis so far. So far, we have assumed, remember, that the collection probability in the depletion region is equal to what? 1, kan? Probability is equal to 1. Okay. However, okay, there's always a but, okay, remember? However, we should consider recombination in optical generation within the volume of the depletion region as well. Setakat ni kita hanya assume the recombination only takes place in the quasi-neutral region, right? True? We assume this, right? Sorry, let me go back. We assume this, right? So it's 1 here and it's lower than 1 to the left and to the right. Is it really 1 here? Well, it's not. Okay? For simplicity, kita assume it's 1. But in the real case, not. So recombination, the physics are not straightforward and better left for advanced course. However, the contribution of recombination in the depletion region results in recombination in the depletion region. Okay? Results in an additional current that flows in parallel to those of N-type and P-type. Okay, you can have a look at the equivalent circuit. Maybe if you have time later on, we'll continue tomorrow. Equivalent circuit of a solar cell. We can discuss later on in the device, in fact, equivalent circuit. Then you can see the factor of recombination of in the depletion region will come into play, right? J recombination in the depletion region, JDR, short circuit, the current density due to the recombination will be given by this J02 exponential of QV over K2 KT, where this denotes the recombination in the depletion region. So before this, we've been assuming that there's no recombination in the depletion region. And this is the JL in the depletion region as well. The physics are here. It's easy to assume if the electric field sweeps all optically generated. Right, if you assume that you also have the optical generation in the depletion region through the width of the W, then the JL will have some contribution from the depletion region as well. Okay, so we're going to come back to this when I talk about the device later on. Ataupun kalau sempat, tomorrow maybe I'll show you on PV CD-ROM, how does it look like when you talk about the collection probability, okay? Because there is a graph as well on the PV CD-ROM which explains in more detail about the collection probability of the carriers. Okay, so that's it for now. It's already 2 p.m. Okay, sorry for that. So tadi we took time a little bit on the presentation explanation. So now we're done with the PN junction under illumination. So tomorrow we're gonna move on to remind me of the PV CD-ROM website to show on the collection probability before we continue with metal semiconductor junction. Okay, is it okay so far? Just a brief intro to the light generated light absorbing device. So when you talk about your photo detectors and your light sensors, solar cells later on in the presentation, you can always come back to this: the junction depth, the doping, the polarity, and the short circuit current and stuff. Right? Okay, all good. So I'll see you tomorrow, inshallah. Bye bye. Take care. Assalamualaikum.